Let me start the recording session again and then see. Okay, so you can hear me, right?
Yes.
Okay. Do you have a specific question number?
Uh, Hold on. We have to go back through it.
Is it a homework or the quiz?
Homework.
Okay.
Because the quiz was pretty easy.
Okay.
Except there's one question that's on it, but it's the same basic question that I have for the other ones. Hold on. Course assignment.
And then the homework will be the other chapter. Let's see. Chapter 11, right?
Yes.
Okay. Let me see. Let me see if I can go ahead and share this. Okay.
Hold on.
Are you seeing my screen?
Hold on. Yes, I see your screen.
Okay. Let me get the No, not that one, not that one. Standard view, all the way to the end. Ignore the words you saw. You are not seeing anything. This is what you're seeing now. So are we on this state right now, this question?
No, that one was pretty easy.
Okay, good.
That
And
one
this,
was pretty easy.
okay. This
That one,
one,
that was easy.
okay, yay. This
Uh,
one,
for sure. That one's pretty easy because it talks about the vapor.
okay, okay. I'm liking this. Mm-hmm. You're using the term,
That one
oh,
right there.
hold on a second. As soon as you said that one right there, it disappeared. Where did it go? Yeah, it's not there. So this one here. Oh, that one?
Yes.
Because we haven't gotten to it yet.
Oh, okay.
Yeah, we haven't gotten to the math part. Now maybe you can do this part here. Have you done
Yeah,
this
I can
part?
do that part.
Yeah, you can do the conceptual part, right?
Yeah.
But the math part, we haven't gotten to it yet. So hopefully tomorrow we get to that part. But since we're here right now and you had a question about that, we can go work it out because it's really not that complicated. What you're doing is, what happened to the equation? Okay, well, you have this equation right here. So I can show you how to work that out. Okay, based on the information, compare the characteristics of the two substances. They gave you a vapor pressure. One is high, one is low. Okay. Yeah, so okay, since we are here and we have the camera on, let's see. Before we do the math, you said you did the first part?
Yes.
Okay, substance A, substance B. A has got a lower vapor pressure. That means there's less vapor at a specific temperature, at room temperature. The second one has a high vapor pressure. So based on that, I guess A is left and B is right. Okay. So drag item to the appropriate bin. Okay, each item. So the one that has less vapor pressure is A. The one that has more is B. I'm trying to make sure I understand this question because you've worked on it. You had time to think about it. I haven't. Okay, let's start with the easier one. Which one has a weaker intermolecular force?
You want to be B?
Yes. That's why the molecules can freely form gas. Which one has a higher boiling point?
Substance A.
Substance A. And we haven't talked about that, but we'll talk about that in when was it? Yeah, we haven't talked about boiling point as it relates to what is it called? Vapor pressure, but we've talked about boiling point as it relates to intermolecular force, right? Based on these numbers here, 275, A has a higher intermolecular force, B has a lower intermolecular force. You can see that, right? So which one has a higher heat of vaporization? Which one did you say?
Nah, that won't be B.
The higher heat of vaporization.
It will be B.
You're saying B?
Yes.
Okay, let's go with that. Which one is a gas at 300?
Oh, hold on. Let me think about that last one again.
Okay.
Has a higher heat evaporation.
The heat required to make a vapor. The heat that you have to add to make a vapor. Most of these heats they're talking to
No,
you about.
substance A. Substance A. There you go.
Okay. Okay. Most of these heats, like boiling point, is similar to heat of vaporization, right? It's heat that you're adding. Same thing with heat of vaporization. Is the heat that you're adding. Okay. It's a gas at 300 milliliter mercury. So it's a gas at a much. So 760 milliliters of mercury is the standard atmospheric pressure. This pressure here is much lower. So which one would you assign this to? That's most likely a gas.
Substance A.
So substance A, the one that has the higher intermolecular force, is the one that you think is a gas. I mean, we're gonna
Oh,
test
okay,
out your
okay,
answers.
I see it. I see what you're saying. So
Mhm.
the vapor pressure, that's what it takes to get to the vapor.
Right.
And the gas is the same thing as a vapor. So
Mhm.
300, so that's not 459, so that's gonna have to be A because it's turning into a gas. So 300, 275, and then 300 milligrams. Yeah, it'll be A.
Okay. Let's. Oh, I see what you're saying. It's a gas at 300 millimeters of mercury.
Yeah.
I see what you're saying. We're gonna try out your answers and then we'll discuss the answers that you have here.
No, one.
Okay. So here's the thing. Wait, how do you reset this? So I don't think this is not the pressure of the gas. They're talking about the surrounding air pressure. I
Okay.
kind of mentioned that, but then I want you to test your own hypotheses. Yeah. So yeah, I was thinking this was the one that was placed wrongly. It's talking about if the atmosphere is more, if you apply a lower pressure, like if you pressurize, this is a fancy way of saying if you pressurize both of them, right? So when you apply pressure to a gas, you have a goal, and the goal is to make it a liquid, right? So instead of saying if you pressurize a gas, which one of these will most likely easily form a liquid, they just ask you which one is still a gas at 300 millimeters mercury. So from here, from what they're saying, you have to think about it that 300 millimeters of mercury is a much higher. It's a no. I'm saying it the other way around. 300 millimeters of mercury is a much lower pressure than atmospheric pressure. Atmospheric pressure is 760, right? So you want to find out which one will be a gas. Here's the bottom line. Instead of thinking about this in a complicated way, one of these two will easily form a gas. The one that has the lower intermolecular force. So all these two, A and B, which one has a lower intermolecular force? Because remember, all these characteristics boil down to intermolecular forces.
Okay, I got you now.
Yeah, which one of the two easily forms gases because it has less intermolecular forces?
Yeah.
That would be B, right? It'd be B. So is there a way to reset this?
Think you just gotta have to drag it.
I have to drag it?
Yeah.
Oh, drag it over like this and then submit? I should know how to do this, right? Oh, yeah, there, right? So when the atmospheric pressure is less, both of these will form gases. But which one is most likely going to form a gas is the one that has lower intermolecular forces because those molecules are not being held by the other molecules very strongly. So yeah. It was just that one little concept. You were thinking this is talking about the pressure of the gas versus the pressure of the atmosphere. Okay. Okay. This is the one that you need the formula for. So since you're here, we can go work it out. Okay. So let me see. Let me pull up my iPad
Because
and I'll copy.
in the formula it talks about, and if you read the book, it says line one P1 over line 1 P2, or is it P1 P1 over P2?
Mm-hmm.
And then
What?
what do you do with the math? How do you do the math for that?
Let me add a page here. Let me see. I'll add a page towards the end because I feel over here. Hold on, hold on.
Yeah, I'm
Delete,
pretty
delete this
decent
word.
with math, but science math just confuses me.
What is science math? Math is math. But no, I understand what you're saying. I understand. I totally get what you're saying. Because science people don't do, it's not that they don't know how to do math. It's just, for science people, math is a means to an end, right? And if you get over the emotions of that, then you're in a much better place as far as understanding why they do things shortcut. So let me write this equation here. Ln of P2 over P1 is equal to delta H vaporization over R, open parentheses, 1 over T1 minus 1 over T2. So in this, let me copy this out first, and then I'll go ahead and oh yeah, so see, I have this ready to go. Let me write this down here, then I'll pull this up. Okay, so I have my equation. It says here in the problem, the vapor pressure of dichloromethane at 0 degrees. So at temperature 1 equals 0 degrees Celsius, the pressure, vapor pressure, P1 is equal to 134 millimeters of mercury. Yeah, we'll get to this later on because it's on slide 68 now. The normal boiling point of dichloromethane is 40 degrees Celsius. So temperature 2 is the normal boiling point. That's 40 degrees Celsius, right? And did they tell us the pressure? They didn't. But when they write normal boiling point, normal means atmospheric pressure. And the atmospheric pressure is 760 millimeters of mercury. So pressure 2 is 760 millimeters of mercury because of the word normal. Normal here means the normal temperature, where normal is what we're used to, so standard, right? So yeah. Oh, I forgot to write the question. We're looking for molar heat of vaporization. We're trying to solve for delta H vap. What is this? Right? So now that I have this here, let me see. The one thing I haven't written here is the value of R. R is 8.314 joules per mole K. And if you go back to the slide right here, they show you R right here. You see that right here? 8.3145. Yeah. That's the molar gas constant. That's the value of R in this context here. Okay. So what you do here is you have log natural P2 over P1. You want to make sure before you even use the formula, the units match, right? They have to map out to each other to make sure you're following dimension analysis. So let me use my highlighter here to match them. This matches with that. I'm good. The Celsius matches with Celsius. But I have an issue because even though T1 and T2 match in units, they don't match the K. The K down here is actually Kelvin. Okay? So it doesn't match this K here. So I technically have to change the temperatures to Kelvin. Let me erase this. Oh, what did I do? Erase that. T1 equals 0 degrees Celsius. T2 equal 40 degrees Celsius. Let me erase that so I can convert it. So, come on. Okay. You want to convert your temperatures to Kelvin, right? Because it has to map out to the Kelvin we have down here. And in most chemistry, I would say 95% of the calculations, the temperature is usually written in Kelvin when you're doing calculations, okay? So 0 plus 273.15, I have 273.15. I don't even know why I used a calculator for that. Anyway, I did. And then that's my first temperature. My second temperature is 40 plus 273.15, 313.15, okay? So I have my two temperatures in the right unit. My pressures match. I am now ready to work on this calculation right here. Okay. So this one, remember, this is the pressure because they use the word normal. When they say normal,
Excuse
that
me.
value is applied. Yeah.
How did you get this number?
The 760.
The 273.15. How did you get that number?
Oh, where do I write this? To go from to get Kelvin from degrees Celsius, you add 273.15.
Okay. All right. All right. Okay.
Yeah,
Now I'm
1411. Uh-huh. Okay. So since I have, let me write this here. Degrees, I mean Kelvin isn't really written as a degree, my bad. It's Kelvin equal degrees Celsius plus 273.15. Okay. So here, where was I? Now that we have this, now we're going to be working on log natural pressure 2 over pressure 1, right? Equal delta H VAP over R 1 over T1 minus 1 over T2. Like I did in 1411. Oh, maybe, no, that's 1412. I keep forgetting. Now I'm forgetting the classes. Let me work on this part first. Then I'll work on this part second. And then work on the one that we're trying to solve for last. Okay? So I'll start with this. Log natural P2 over P1 is equal to log natural, what's pressure 2? Pressure 2 is 760 millimeters of mercury over, where's pressure 1? 134 millimeters of mercury. Okay? So I got 760 divided by 134. So I have log natural of 5.67, which is equal to, where's my log natural? Second log to the right, number 1. The previous answer. Yeah, it's complicated like that. That's what I get for buying a cheap calculator. You know what, y'all? I'm happy, so I'm good. 1.735. Okay? So I have this part done. This is 1.735. Now for the other part, I'm going to be working. I need more space. It's okay. I'm adding more space, but I want to be organized so y'all can see what I'm working on. Now I'm working on the other part, the 1 over T1 minus 1 over T2. I'm working on this part next, right? 1 over, what's my temperature 1? Temperature 1 was 273.15 minus 1 over, is it 313? Yeah, 313.15. These are both Kelvin. Okay, I'm going to plug this in my calculator. Now, my calculator has a fraction feature. So I'll say open parentheses just to be safe because I want to make sure this is good. I write the number down here. 1 fraction 273.15 to the right minus 1 fraction 313.15 to the right, close parentheses. What do they give me? Okay, I got 0.000467634. Yeah, I wrote it all. I know, I wrote it all. Okay, essentially that's this number right here, 0.000467634. Okay, so to simplify my math, now write it as 1.735, right? Which is essentially this number right here, equal delta H VAP over R times 0.000467634. I know what R is. I already have those units. Now I have to solve for delta H VAP. Okay, but before I do all that, I will divide by this number, both sides, 0.000467634. Divide this both sides, 0.000467634. So I can cancel that out. I have my answer on my calculator. Divide by 1.735. I don't like retyping answers, so I just kind of, yeah, divide it in there, and then I do the inverse of. So, so right now I have 3710, and then this is delta H VAP over R. I know that R is equal to 8.314 joules per mole Kelvin. So I can plug that in here and solve for delta H VAP. 3710 times R equal delta H VAP. Just in case you're wondering, I multiplied R both sides times R. So this can cancel out. Okay? 3710 times finally the value of R, which is 8.314 equal delta H VAP. And this is times 8.314, which gives me 30846 joules per mole, delta H VAP. Now, many times delta H VAP is written in kilojoules. Let me check to see what the units are here. Oh, they didn't give me the units. Most of the time when I've seen delta H VAP, delta H enthalpy, it's written as kilojoules. So you can write the answer this way, or take the 30846 joules per mole and then take the number 1 kilojoule divided by 1000 joules, and that gives you the answer. Divide by 1000. Like that. It gives you 30.84 kilojoules per mole. So you can enter either one, but it has to be consistent with the units. So we can enter this second answer here, or the first one here. As long as the units are right, I think it should accept it, right? Here's the other thing I have to check. How many significant figures are we working with? I keep forgetting. Okay, this is 3. 1, 3, 4. This is 3 sig figs. But you see this number? That makes that 0 significant. So we have to have 2. This is 3 significant figures. This is 2. So we need only 2 significant figures. So I need to rewrite this technically as approximately right here 31000 joules per mole. I have to round this up because this number here, 40 point, makes the 0 significant. Why? 1411 rules. In 1411 rules of significant figure, so rule, I write the rule right here. A 0 with a non-zero number to its left and a decimal to its right is significant. Okay, so if you have, oh, I just realized the screen is kind of to the left. Yeah, so a 0, when you have a 0 with a non-zero number to its left and a decimal to its right is significant. So the 40 point counts as 2 significant figures. So I took this number, remember the 3 counts as significant. This position counts as significant. So all these numbers have to be rounded off. To do that, since the number to the right of the 0, the last significant number or position is 0, right? The number to the right of that is 8. You have to round up and then drop off the remaining numbers. You don't really drop them off. I would say replace them with 0. So this number becomes 3. This position remains as 3. This changes to 1 because you round it up from here. Then the 846 now becomes 0, 0, 0. Then down here, same thing. This position remains. This position remains. Round up, and we end up with 31 kilojoules per mole. Okay, finally, let's see. After all this work, they better say yes, or I'm calling somebody. Okay. So on my end, I get 31. Yeah. And then I put here, I think it's small, kilojoules is small k. And A over MOL. I hope that works. Please say it works. Yes. Yeah, whatever. It's rounded differently. It's rounded correctly, okay?
Thank
Anyway.
goodness you did this question because it blew my mind.
Because we haven't worked on it yet in class. We'll get to it tomorrow.
Now, I got another question for you. Now, is it possible for you to be missing the HVAP from the equation? And how do you do it if they got it missing from the equation? Like the HVAP is not in that location, but in a different location. Like to
This
the left.
HVAC,
Yes.
can
Or
it be to the left?
yeah. You're trying to find HVAP.
Oh, I was trying to find HVAC though.
Oh, okay. Or
Yeah.
like another one, like find P2.
Ah. Why you gotta mix it up, bro? Why you gotta mix it up? Okay, let's
Because
see.
I'm really good at math and I like to know questions.
Okay,
But
so
like it says
this one here.
find T1, like find T1.
Okay, so you want me to rearrange?
Yeah, how what happens if they rearrange it or you're trying to find T1
Then
and
you rearrange it.
but what does it just okay, just a plug? All right, I got what you're saying.
Right. So
Okay,
I rearranged this based on what I was looking for. So what I mean by this, right? To me, I view that equation as having three different parts. You
okay.
know, three significant parts. So I break it down that way. I mean, I can do it without all that math, but as a teacher, when I'm illustrating it, I like to view it as three, not equal parts, but three parts, right? You have the log natural part, the P2 over to P1, where there's a parenthesis here. You have the HVAC part, this part here, over R. And then you have the temperature part, T1 minus T2. So the question they're asking you will usually have an unknown, either in this region here, here, or here. So I get what you're saying. So since I see this equation as having three different parts, if the unknown is right here, I work all these first before I do the last part. So say the unknown is
Okay.
here,
All
and
right.
say we're solving. How do you spell unknown again? Listen, I I start talking, I start getting into chemistry, and I forget English, I forget left and right. Okay, let's say they're saying solve for T1. How about that? Woo!
Don't worry. Like I'm really good at math, but I'm horrible in English.
Right, because I'm like I forgot how to spell unknown. I panicked for a second there. So let's say they're telling you to solve for T1. What I would do at that point, I would do this part first. I will do this second part second, and then I'll take 1 divided by 2, whatever number I get there, and then that makes it equal to 1 over T1 minus 1 over like this. You see what I'm saying? So then I get a number here, and then I can rearrange accordingly. Does that make sense?
Yes, it does. Now it does. Thank you.
Yeah, so I try to break it down because I'm like, to me, you can solve math in a complicated way, and that's great, but it takes a lot to really break it down and make it simple,
Mm.
and then go from there. So let me see. Let me see if I can use the numbers we had to try to come up with something else.
No,
So
I
I'm
think
gonna.
I got it. I got it now. I'm
You
good.
got it?
Yeah, yeah.
Okay, okay, okay. I try not to overteach because I've been accused by loved ones, that's AKA my brother, that I overteach or I overexplain.
No, no, that's good for me. I'm a veteran. I like to learn like a lot more, and then like like that's especially what I did in the military. Like whenever it came down to asking like questions, I used to always ask my superior questions. The more questions,
Right,
the better. So
right, right. Huh? Tell me about it.
yeah.
Mhm.
So
Okay, so yeah, we'll be working on that question tomorrow, right here. We'll be solving for P1 right here. You can see that?
okay.
Yeah. So I still want to say this for tomorrow because I want to record it under chapter whatever part 3, right?
Yeah.
Okay. What else?
Well, the other questions were the ones on that right there. Could you go to
Mm,
number 7?
Seriously, seriously.
Yeah, some of them
See,
not.
these are not that bad, right?
Yeah,
Oh, this one is also one of those questions where we haven't, but that's okay. Since you're here right now, I'll go over it with you. So when we go over it in class tomorrow, then class will be like a review, right?
correct.
Yeah, we haven't done this one here. I wish I can copy here and paste there, but it doesn't work. I can't copy from here to that because yeah, this is just projecting. Ah, okay. I have to write this down. Let me not be lazy. I can do this, like for real. I can do this. Let me add a couple of pages. Add a page. Add a page. Let me see. I see a lot of words. Add a third page. There's a lot of math in 1412, but if you love math, it would be great. Okay, so
Not
here the
science math.
okay. So let me try to explain this without teaching it, if that makes sense. Because tomorrow I'm going to be teaching it in context. So one of the goals of this class, besides a lot of other things, at this point now we're not even looking at intermolecular forces anymore. We've kind of stepped back a little bit, and we're seeing how all of this plays out in quote unquote real life in the industry. So one of the things that scientists do in industry is heat different chemicals. And if you're in industry, heating is money. It costs money to heat chemicals. So you want to know early on how much heat it takes to accomplish some kind of physical change, right? So here they're asking you how much heat in kilojoules. So I'm going to write here how much heat in kilojoules is required to warm 13 grams of ice. So I'm not going to write all the words. What I'm going to start writing now is what we're looking for. We're calculating heat, and heat has a symbol Q, just like we did in 1411. The units are kilojoules. And it's saying it's required to warm 13 grams of ice. So our mass here of ice, and ice is just really, really cold water, right? It's going to be 13.0 grams. So I have this written down. I'm writing them all up here of ice. Initially at temperature 1 is negative 10 degrees Celsius to steam. All right, to steam at 109 degrees or zero point 0 degrees Celsius. Okay, so it's 10.0. I'm trying to remember this question because it's been a while since I've worked here. The last time I taught 1412 was summer, so I'm trying to think back. Okay, the heat capacity of ice is 2.09, and I guess these all have the same unit, joules per gram per degree Celsius. Heat capacity, so I'm writing this one here, of water is this number. I like to itemize it. So of water is 4.18 joules per gram per degree Celsius. Then heat capacity of steam, as it says right here, steam, because they said ice, water, steam, and they wrote the number back to back. But I like to go ice, this number, water, this number, steam, this number. So steam is equal to 2.01 joules per gram per degree Celsius, okay, respectively. So I'm right here. The enthalpy of fusion of ice is, so delta H fusion, okay? So there's so many different delta H's. Delta H's is just the amount of heat required to accomplish a task, right? So we earlier learned about the heat of vaporization, and that will be written as delta H vap. And then if you're trying to either melt a solid or freeze a liquid, it's called delta H of fusion. And this is given to us as 6020 joules per mole. And this is for ice. So it looks like we're either freezing ice or we're melting ice. And the enthalpy of vaporization, delta H vaporization, usually this is of liquid water. This is 40700 joules per mole. Yeah. No, I would say you accurately said chemistry math, because chemistry math or science math is not like math, right? Usually math majors sit in my class and they cringe, like, what are you doing to math? I'm like, using.
Yeah, I told you it's chemistry math.
Right, they look at me like you're ruining it. I'm like, I'm not ruining it. We're just using it and we're discarding it when we're done. Okay. And we take shortcuts that don't sound right, but it works for us. Okay. Anyway, where was I? So this is the question. Now, I usually say when you're working this question out, don't think back to 1411 where you had that Q is equal to mcs delta T and just apply that, because if you try this, it's not going to work. This question is a lot more complex than what we covered in 1411. This question has got quite a few stages, okay? So I'm going to draw a picture, a graph that illustrates all the transformational changes we see as we take a piece of ice and we heat it up. So on the right, we have the progress. Oh, sorry, I guess we can call it heat added. Then on the top, we have temp temperature. Okay, when I say top, I mean left. Here, this is temperature. And on the right or horizontal axis, we'll call this the progress, right? I'm trying to think about a word, but I can't think about it right now. Oh, yeah, it is heat added. Heat added. I'm a little rusty. Heat added. Okay, there. So the question started with negative 10 degrees Celsius. So on your x, I'm sorry, this is a y-axis. On your y-axis, you want to mark negative 10 degrees Celsius. Since we're starting with a solid that's frozen, you want to understand that when you take a frozen solid and you're trying to get it to steam, it doesn't go from solid ice, especially in this case water, directly to steam. It actually melts first. So in the graph I'm about to draw here, I have to include melting point and boiling point. Okay? So remember, for ice, we know that the melting point for ice, or the freezing point, is 0 degrees Celsius. I don't know how I wrote that. 0 degrees Celsius, right? And then as far as water is concerned, the boiling point of water is around 100 degrees Celsius. These points have to be part of your graph. So we have negative 10. I'm going to include 0 degrees Celsius because we have a phase change. Remember, phase is like state, solid, liquid, gas. When we get to 100, 100 is right here. Boiling happens at 100 degrees Celsius. So I have included that. I've included that. Then they said everything finally ends at 109 degrees. So I'm going to report that too here. Okay, they gave us two temperatures, the starting point and the ending point, but I'm telling you, because we're starting with the frozen solid, we have to include two more, the freezing point or the melting point and the boiling point. So I went ahead and included that. Okay, when it comes to the graph, we have to remember, which I'll talk about this again tomorrow when we talk about the actual lesson in context. As you're applying heat is being applied, right? And when you look at, if you actually measure the ice, the ice will start to get warm and warm and warm. So all the heat that's being applied is being used to heat. I didn't have a plan to do that. The app does it automatically. Okay, I'll write it like this. So all the heat you're applying until it gets to 0 degrees Celsius is being used to heat up the ice. Once you hit 0 degrees Celsius, all the heat added at that point now has a new purpose. It doesn't heat up the ice anymore. It actually converts the solid ice to liquid water. So at 0 degrees Celsius, we see a phase change from solid to liquid. So we're starting with the ice being a solid, right? So we go from solid to solid where the temperature is increasing as the ice gets warmer. It goes from super cold to kind of, not kind of cold, but cold, frozen cold. From here to here, we see a phase change where solid ice or solid water becomes liquid water. Then you keep adding heat. As you continue to add heat, Now the water starts to get hot. I have to draw this fast or else it would change. Hold on. I'm at 100. Oh, I'm a little bit over 100. Hold on. Let me do this again. I go up to 100 right there. Once again, it will still be in a liquid state. When you hit the 100 mark, the liquid begins to form gas. This actually takes more energy, right? Because I told you guys last week, it takes more energy to make a gas from a liquid because you have to make sure the molecules of gas or vapor get enough energy to stay away from each other. They have to be far away from each other, remain far away from each other to be gas phase. So you have to heat the molecules, energize them a lot. So the amount of heat added here, you can see, is a lot. At this point, we go from liquid to gas. Once we get to gas, you heat this up some more, a little bit more, and we get from hot gas to really, really hot gas. Okay? So I have drawn a picture of the 5 stages a solid chemical goes to form steam. I'll call this 1, 2, 3, 4, 5. What the question is asking you is, what is the overall energy required to go from step 1 all the way to step 5? Okay, so we'll figure out the heat for step 1, step 2, or segment 1, segment 2, segment 3, segment 4, and segment 5, and then we'll go ahead and add them all up. So the question they're asking you, okay, let me write this here, 0 degrees Celsius, 100 degrees Celsius. The heat total, or total heat, is essentially heat at step 1 plus heat at step 2 plus heat at step 3 plus heat at step 4 plus heat at step 5. Okay? Pretty straightforward, right? Figure out the whole, because if they were starting from the middle, we would start from there, but they're starting from what I call the beginning. Okay? You're with me so far?
Sam.
Okay. Now all we need is a formula. So for Q1, Q2, and Q1, Q2, and Q3 and Q5, we will use the following formula. Q equal MCS delta T. Okay? For the odd numbers, Q1, Q3, Q5. So looking at the picture, how do you know? I'm going to write that right here. Let me use different colors, okay? I'll use yellow for the first one. This would be Q equal MC ice delta T. And this is going to be the first one right here, the first equation. For the third equation, Q equal MC liquid delta T. Let me think of a different color. Green. And number 5 up here, Q equal M C, what's gas? Delta T. Okay. For the 3 different states of matter, what color do I want? It's just a struggle. Let's go with pink. Pink is too dark. I want you guys to see it. So gray. Yeah, gray works. Okay. But what about the even number transformations? What do step 1, step 2, and step 3 have in common? If you look at them, they have 2 temperatures, right? You see they have 2 temperatures? Step 1 goes from -10 to 0. Step 3 goes from 0 to 100. Step 5 goes from 100 to 109. Do you see what I'm talking about?
Yes.
Right. So the odd numbers have 2 different temperatures, so we can use this formula. The even numbers don't have 2 different temperatures. 2 starts at 0, ends at 0. So if you use that formula, you get 0, and that would be wrong because you see how you're going from here to here? You are adding heat. This formula will not work anymore. So we have to use a different formula. So for step 2, we use Q is equal to N, where N is number of moles, delta H fusion. So remember, fusion happens during freezing, during cold environment. Fusion just means going from fusion is like freezing. So you're going from liquid to solid or solid to liquid. I have to think about what freezing is. Yeah, fusion. Okay. And then boiling, forming a vapor, goes with vaporization. So over here, same thing. Q equal N delta H vap. Because in thermodynamic language, which is like another section of chemistry, right, with special chemists, they use the term vaporization in the place of boiling or in the place of forming a vapor. So most of the time in general chemistry, you just say boiling or freezing, but the correct terminology in thermodynamics, which applies here, is vaporization and fusion. Okay? So you see how I have this in the right place? So we're going to be using these formulas to figure out the Q's. Once we're done, we add them all up. You good?
Yes, I'm good.
Okay, let's do this. Where are my numbers? Oh, my numbers are up here. Now that I have this, let me see how I can help myself here. Copy this list. Now write this down here. Okay. Okay. I have my mass of ice in grams. But you see how these formulas here, they have N for moles. So what I'm going to do is make life easy for myself and get the mass of, not the mass, sorry, get the moles of ice so that whenever I need it, I will use the moles versus the mass, right? Remember, M here stands for mass. Now I need the moles of ice. To get the moles of ice, what I'm going to do here is convert the mass to moles. I'll take 13.0 grams divided by 18 grams per mole. Once again, 1411. 1412 is like 1411 applied. If I was to say it in one phrase, it would be like, everything you learned and probably forgotten 1411. Yeah, it's been applied to harder things.
So how'd you get the 18 grams the most?
Okay, so let me write this down here so I can have like a linear flow.
Got
Molar
it.
mass of water. You just remembered it? H2O, two hydrogens,
Oh,
one
okay.
oxygen.
Yeah, H2.
Uh-huh.
Yes, 18 grams.
16, 18 grams
Okay, I got it.
from the periodic table. This is good though. It's, some people probably will have the same question. So yeah, we got that. So having this, the number of moles of ice, which is technically water, is, what was the mass again? 13 grams divided by 18 point, nah, it doesn't matter, 0 grams per mole. You can see here, grams and grams cancel out. We're left with moles, right? 13 divided by 18. I'm using my calculator. I own up to it, 0.722 moles. Okay, so whenever I need moles of either ice or whatever, whenever I need moles, I'm using this number. Okay, when I need moles. Okay, I'm ready to go. Let's start with the first one. So the first one, this is the formula I'm using. I'm going to underline it as I use it. I'm using this, QM ice delta T. So starting with the first one, Q1 is equal to M of course, the ice, right? C ice delta T. So remember I told you guys, we're only working on segment 1, this part right here. That's it, just that part. We're going from -10 to 0. So over here, I'll say my temperature 1 is -10 degrees Celsius. My temperature 2 is 0 degrees Celsius. Don't skip and go all the way to the end. I've seen some people, Just use -10 to 109. You can't skip. There's 5 different steps and they have to be done separately. Okay? So from this, I can say my delta T is T2 minus T1. What is T2 minus T1? 0 minus 10 degrees Celsius. That gives me what? 10 degrees Celsius, right? Because you're doing it like this. Minus times minus is positive. So I have this part of the equation done. Was I given C of I? See, I was. I didn't want to go all the way back, this number right here. So I'm going to recopy it. C of ice is 2.09 joules per gram per degree Celsius. Yep, I got this. And the mass was, what, 13 grams? I got that. I just rewrite it here because it just makes me feel better. It's a small thing. So I got all the numbers I needed right here. I'm not having to scroll back and forth. So Q1 is equal to, and the units will work out. Remember Q from 1411 is measured in joules. So when you work out your math, if you get your answer in joules, you can feel better knowing that you got the units you're supposed to get. If the units don't work out, something is very wrong. My mass is 3.0 grams, right? Times C ice, where's C ice? 2.09 joules per gram per degree Celsius times delta T is right here, 10 degrees Celsius. Grams, grams, degrees Celsius, degrees Celsius. My answer will be in joules. I'm already feeling better, already having vibes of good vibes. 13 times 2.09 times 10. So my first number is 271.7 joules. I have Q1. Okay. Remember, we're starting from the molecule being or from the water being in ice form. So everything had to go with ice. Okay, I'm doing Q2 next. Q2. Now Q2 is what the flat level, right? I have to use number of moles of ice, delta H fusion, because fusion is consistent with ice. So do I have number of moles of ice already? Yes, I have that. That will be 0.722, just 22 moles. I have that number times. What's delta H fusion of ice? Delta H fusion, do I have it somewhere down here? I already used this number. Delta H fusion, 6020 joules per mole. So I'm going to use that one. 6020 joules per mole. Was that it for the units? Yep, 6020. Okay, once again, if you work out your Q and your answer ends up with the units joules, you can feel just a little bit confident, okay, that you are in the right neighborhood of the answer. If your units don't work out right, you should feel very, very afraid. 0.722 times 6020, bam, got the answer right here for my second Q2 for 346.44. Okay, you with me so far?
Yes.
Okay, so we got 2 Qs. We got 3 more to go. Okay, where was I? I did that one. I did that one. I'm done with this. I'm done with this. Now I'm here. I'm going from, as far as the progress is concerned, from 0 to 100. So I have to do the liquid stuff. Okay, I can do this. Q3 is mass of liquid water, C of liquid water, delta T. This time from the picture, my initial temperature was 0 degrees Celsius, and that's going all the way to 100 degrees Celsius. So my delta T is going to be 100 minus 0, which is going to be 100 degrees Celsius. Okay, final minus initial, right? Okay, so I got delta T. Oh, my mass is still, mass of liquid is the same as the mass of the ice. It doesn't change. It's still 13.0 grams. C of the liquid water, I think it was 4.18. Let's see, where was it? 4.18. Okay, so I'm using that number, joules per gram. 4.18 joules per gram per degree Celsius. Okay, let's do this. Now that I have this, Q3 is 13.0 grams times 4.18 joules per grams per degree Celsius times, we got this up here, right? 100 grams and grams cancel out. C and C, degrees Celsius, cancel out. Once again, we got our answer in joules. Every time I get the units right, do you know I hated dimension analysis? You can't tell right now, right? It's all in the past. I hated it, and then one day I just started loving it. I'm like, oh my goodness, how did I hate this? I had a way of working things out, and I wanted to stick with that. I didn't realize the power of dimension analysis. Then once I realized the power, I was thinking, what was I thinking, young self? I got 5,434. That's what I got. Let me make sure. 13 times 4.1. I said times and I wrote plus. Times 100. Yeah. 3, right? Q1, Q2, Q3. We got 3 more to go. I mean, sorry, 2 more to go. Now Q4. Q4, once again, is that flat region in the graph. So I'm done with this part here. I'm done with this one here. We're now in that flat region in the graph, but we're dealing with vaporization of water. So that's the equation I'm going to be dealing with. So Q4 is number of moles of, let's see, Q4 is in the liquid state as we're forming a vapor. And then delta H, this time of vaporization, because we're going from a liquid state to a gas state. So I need to find delta H of vaporization. I had it somewhere here. There it is, 40700. Okay, this is going to be 40700 joules per mole. Okay. Number of moles of the liquid. The number of moles of the gas is the same thing as the number of moles of the liquid, same thing as the number of moles of the solid. So I just need to find where I did moles. Oh, right here. Number of moles of ice is the same thing as the number of moles of the other 2 states. It's not changing. We're assuming it's not vaporizing. So I'm just going to copy 0.722. 0.722 moles, right? As the number of moles of liquid is same as all the other states. Q4. Okay, moles cancel out. Our answer will be in joules, whatever it is. We're in the right track. 0.722 times, what's the number? 4,700, 40700. Okay, I'm saying it wrong, but I know I'm typing it right. So this is 29385, right? That's a lot of energy. Remember that question I asked you guys last time? Which one requires more energy, melting a solid or making a vapor from a liquid? You can see right now. Look at how huge that number is. Look at how huge Q4 is compared to Q2, right? Huge. It takes a lot more energy to make a gas out of a liquid. Okay, moving on. Our last step, Q5. Q5. And I can separate this visually if that's necessary. This is Q4 right there. And then where is Q3? Right there. We got Q2. Where's Q1? Q1 is right there. Okay. Okay, we are doing Q5. Q5 in the graph is that last segment where we have a temperature change. So right here, from 100 to 109. So now we're dealing with gas phase, right? So Q5, you have M, this time of the gas, gaseous water, C of the gas, delta T, okay? Temperature 1 was 100. Temperature 2 is going to be 109. Oh, I keep writing further and further right like I have all this unlimited space. I don't know why I do that, but I do. I do it. Delta T is 109, final step, or final temperature minus initial temperature, degrees Celsius, minus 100 degrees Celsius. So Our difference here is 9 degrees Celsius, right? 109 minus 100. Okay, let's see what the damage is. We got delta T. We got that. C of gas. C of gas. Let's see. I'll write it here. C gas. I'm trying not to add a page. I may have to still add a page. Oh, steam. 2.01 right there. 2.01 joules per gram per degree Celsius. So as far as the mass is concerned, I have 9 degrees Celsius, 2.01 joules per gram per degree Celsius. Now I need the mass. Mass has not changed, 13.0 grams. Okay. We're assuming that the liquid is not vaporizing, so the mass they gave in the beginning is constant, traveling through the different phases, right? So gram, gram cancels out. Celsius, Celsius cancels out. Once again, your answer is going to be in joules. So we got 13 times 2.01 times 9, and we end up with 235.17. Not much at all, right? Because you already have the vapor in the highest, most energized state. All you're doing is just heating it up. Okay, so 13 times 2.01 times 9. Yep. Okay, now Q total is the sum of all of these. So I'm going to say here, where's Q1? 271.7. 271.7 joules plus 4346.44. 4346.44. Trying to figure out, do I even need those last numbers? But you know how what is it called? Mastering chemistry reports you, not reports you like to anybody, but like you round it out differently. Like I don't know. I kind of feel like I'm being judged at that point. And I talk back. It's not even that serious. But anyway, 5434. I'm like, you can't tell me what to do. And then 29385. 29385 joules. And then finally we have 235.17 joules. We have to add all of these up. So let me see. Can I do this? The answer plus, let me start from the beginning. 271.7 plus 4346.44 plus 5434 plus 29385 plus 235.17. I hope I typed this in right, because I end up with 39672. I'll leave the last, let's just say joules. This is what I end up with. So let me check the numbers and see the significant figures, because this is 5, 1, 2, 3, 4, 5. Let me see the numbers they gave us. Okay, these are 3 sig figs. 1, 2, 3, 4. So 3 wins over 4. These are 3 wins over 4. This is 3. This is 3, 3, 3, 3. Okay, the winner is 3 sig figs. So I compared all the numbers, right? And the least significant figures I saw was 3. So now back to this number. How do I round this number up or down for it to have 3 sig figs? This position makes it, this position makes it, this one makes it. You start counting from the left, right? You have to drop 7 and 2. Since the first position that doesn't make it has a number greater than 5, I have to round up, right? So 3 remains as is, 9 as is, 6 becomes 7, and then this becomes 0, 0. You drop the numbers off, but you replace 0 with that position, or replace the numbers with 0. Okay? So let's see how they have this. Do they have units for me? Are you kidding me? They have units, kilojoules. I forgot. This is my bad. So I have to convert to kilojoules, divide by 1,000. Right? That's the shortest way. Divide by 1,000, move the decimal right here. I'm going to do a shorthand because I'm out of space and I refuse to add one more page. That becomes kilojoules. So it becomes 39.7 kilojoules. Okay. 39.7 kilojoules. This becomes the right significant figures. Okay. Let me change this one here back to joules because now it's bothering me. 39700 joules, and that's kilojoules. Okay, let's try this. This better be right. If it's not right, they're not really keeping a score of my performance. I just like the affirmation thing. We did do a lot of math. Please say it's right.
Oh, we did.
Oh my goodness, what is all of that? See how they always have to write was either rounded differently, yeah. But look at how they work it out. Oh, they got 39.6. Okay, but you see how they worked it out, right? Step by step.
Yeah.
I don't know why they leave out the picture. I love that little graph we draw because it helps you to see why you don't just jump from the beginning to the final, but you do Q1, Q2. They kind of randomize it, right? Q3, Q4, Q5. What about Q1 and Q2? Oh well. Yep, there it is. Yeah, any other question?
All right, you're gonna hate me for this one.
Oh yeah, I'm already What am I gonna hate you for?
Yes, it's on 1411. How do you find the group number to the molecule?
Oh, to do the Lewis structure thing?
Yes. How do you find it again? It blew my
Okay,
mind.
hold on. What I'm trying to figure out here is not that. Oh, by the way, this question, you see how this question has the phases? See,
Yes.
1, 2, 3, yeah. So this is based on the other one, and you can see all the little numbers they have here. Let me see. Oh, okay. So are we done with the homework questions?
Yes. Homework questions were good.
Okay. Um. Let me go with group numbers. There is a lot of stuff online, right? Which is both good and bad. It's good because there's resources out there. It's bad because there's too much and you have to find just the right thing. So let me start navigating here. Uh, the group numbers. I'm trying to go with the old school one. What is all of this? This is
The one to the left.
uh. There's a new way of numbering the groups that makes it more complicated. There is this. There's this one here, which essentially go by the elements. Okay, this is not very helpful, but yeah, like group 1A, 2A, 3A, and stuff like that. But this one doesn't have the actual elements in there. So let
Oh,
me see the.
so we just go where the number is, and then that's where we find like how many. Okay.
Right, but you're only estimating for the A group, not B group. You know what? Let me use the new one. We can do this. When I
Okay.
say we, I mostly mean me. Yeah. So, you know what? Hold on a second. I forgot. I actually need to do it on my iPad because I want to write on it. I use so much technology, I suddenly and get confused. Because I cannot write on the computer screen. I can write on my iPad. So let me find the iPad and I can show you. But yeah, it's based on the group position. So let me look for the printable one. It's a lot more simpler and easier to follow with. Nobody wants to buy the periodic table. Let me see if this one here works. Uh, okay. You see that, right?
Yes.
Oh. So
It's not showing like the 3A, 3B, right?
yeah, it's not showing you the A's and the B's. I don't know. But Hydrogen is in group one, beryllium group two. Then you skip over the block right here from, oh snap, from scandium, and then you see how 13, 13,
Mm-hmm.
that's the new way they do group three. So what I do, I just ignore the number before the, I ignore the one and only so boron, aluminum, gallium. Oh, as I'm touching, but boron, aluminum, gallium is in group three. Okay, I
Okay.
don't know how to do this, but yeah, you get what I'm saying.
Yeah.
So what I do, I find the periodic table online. I print it out. I don't know. I'm gonna be finding it very soon. My desk is neat, but I can't find anything.
Mm-hmm.
Yeah, so boron, aluminum, they're all in group three. Then carbon is in group four, silicon in group four, nitrogen group five. So I just ignore the one. Oh, that's advertising. I ignore the one before, like the 13, 14, 15, 16, 17.
Yeah.
Now they're doing this whole new way of doing things, and I'm like, what happened to the old way? I like the old way.
Mm.
Where boron is 13, carbon is 14, nitrogen, oxygen, fluorine, and then helium is, sorry, when I say 13, I mean 3, 4, 5, 6, 7, 8. And helium and the rest of them are group 8.
All right.
So go by those group numbers, right? So the group numbers are your valence electrons.
Okay. All right. Now it makes sense.
Yeah.
Well, that's basically it for today. I think you helped me out so much, so thank you.
Oh, you're welcome. So here's the thing. To make sure you don't forget all of this, take organic. What is this? This is spring, right?
Mm-hmm.
Take organic right after.
Are you
Because
teaching organic?
no, bruh, no.
What's
No,
next?
organic is a beast.
Uh,
No, I taught organic in my younger years.
dang. Who do you recommend for organic then?
Well, we have two teachers that teach organic, organic one and organic two.
Oh, okay. This is
Yeah.
only some people. Are they pretty easy to teach, or is
No,
it
organic is complex. That's why I don't teach it. It's not it's different from 14, 11, 14, 12. It's just very there's no math in it. There's not a
oh
whole lot of math. It's more like to me it's like puzzles, logic.
so fun?
Did I enjoy the class? Oh yeah. Did it challenge me? Yeah. Did it make me cry some days?
Yeah.
But it's it does stretch your mind, right? There's not a
Mm.
lot of math. All of a sudden, you're in organic chemistry class missing 14, 12, thinking, oh yeah. But once you figure out the logic and how it works, it's a great class. What
Oh.
we did earlier to figure out which molecule had a higher boiling point, that's just a little introduction to into organic. There
Mm.
are rules, but there are many molecules that don't follow the rules. So you have to know the rule, you have to know how to apply it, and then you have to know what elements and compounds do not follow the rule, and you have to know why,
All right.
right? So when I understood organic from the point of view of me being an advocate and trying to explain why this molecule doesn't obey the rule, why it doesn't have to obey the rule, it made me kind of understand what I was doing better. It took me a while to really get organic because we started doing organic in middle school, and you're like, what? But it was like baby organic. But it was like okay. But by the time I got to the end of middle school, I think I had the sense of it. I understood what was going on, and then by high school, it was a lot easier.
Then they made you take English?
Yeah, because the books were written in English. How am I supposed to
Man,
read?
I'll tell you,
What
man,
is
America
it?
needs to step it up.
You what?
America needs to step it up.
Well, I mean, you're reading the book in English, and they don't translate that to Swahili, right? Because it's a global world. So when you write your paper in your own language, that limits who can read it, right? And Africa being a continent, well, when I left, there were 49 countries. Now there are more than 50 something countries. You can't, yeah, you want to make sure that the works that you publish can be partaken or other people from different countries can read it. If they have to learn your language to read it, they will less likely look at your work. And that limits you, right? So what we do is we adapt and we just learn things, in English. Other countries that are French speaking countries, they will usually learn it in French. And science is a lot easier, I would say, because most of the science words are usually in have a Latin base, so it makes it easier. If you're doing sociology, it's harder to go from one language to another because we're using a lot of Latin based, like yeah, Latin based naming nomenclature and stuff like that. But most of the time, when it comes to science and stuff, we had to learn it in English. I mean, it would have been really tough. I mean, a teacher could try to explain to you what's going on in the local language, but ultimately you have to be able to communicate it in English. Yeah, but
Too bad the math's
the,
not the same. If the math was all the same, it would be universal.
no, the math was the same. No, the math was the same, and the math is what really helped because it's just numbers. But the
I'm
math,
talking about chemistry math. Too bad chemistry math is not the like regular math.
it can't be just like in chemistry English is not like regular English, right? The terminology they use in chemistry serves a purpose for the chemist. The math used in chemistry serves the purpose for the chemist. Once again, it really all boils down to the world of chemistry and the chemist. So there's some things we will do to the quadratic equation that will bother math people. And at that point, I'll apologize. I'll say, if I hurt your feelings, I'm sorry. But this is what we do. We have a purpose. It doesn't work. Right. There's a lot of approximations that we make in chemistry math that allows us to get away with what we're doing because it has to work with the world of chemistry. And some stuff we do for convenience too, right? So
Yeah.
same thing with the languages. When it comes to a word like precipitation, outside of chemistry, precipitation means little droplets forming big droplets when you're dealing with rain, right? A mist coagulating together to form droplets. But in chemistry, that same word means something totally different. Well, the process is somewhat similar-ish. Not really, because you're having a solid form. So when a solid is forming, that's something completely different than forming a liquid droplets. So yeah, the English and chemistry is slightly different, and then you have to kind of learn it in the context. So yeah, once I learned that, it made things easier because I just thought the math was the same. I thought the English was the same, then I realized it's not. It's contextual. It's based on the context. Even the letters, right? You have a lot of M's and N's in chemistry that have different meanings in different chapters. So you want to learn all that in this chapter. This is what M means. In a different chapter, M means something different. So when you learn that, it makes it a lot easier. Because it took me a while to realize why y'all using the same letter. There's like how many alphabets in the letter? Like how many alphabets do we have? Can we use others? Why are we using N again? Why are we using M for the 100th time? Well, that was me exaggerating, but you know what I'm saying? But it took me a while to realize context. Okay, context. Because we're learning this in middle school. But anyway, is that it? Are we done?
Yeah, we're good. Thank you so much.
Yay. Okay. Well, I'll see you again tomorrow. Man. Okay.
Okay. All right.
I
Thank
know.
you. All right. Bye.
Okay. Bye.